Last lecture, we spoke about feature extractors and feature descriptors. In particular, we spoke about SIFT and its variants. Before we go to other kinds of features, we'll take a slight detour and talk about another important task in processing of images, which is image segmentation. Human vision has been studied extensively from several perspectives, and one of the perspectives of human perception has been based on what is known as the Gestalt theory, which emerged almost 100 years ago, which had this fundamental principle that the whole is greater than the sum of its parts. And one of the important cornerstones of this theory was the idea of grouping to understand human vision. So this is a very popular optical illusion. It's known as the Mueller-Lyer illusion, which asks a viewer as to which of these horizontal lines is longer. And because of the human perception's bias towards viewing things as a group and not the individual components, the illusion actually arises here and makes one line look longer than the other, while the horizontal lines are exactly the same length in both of these images. So Gestalt theory proposes various factors in images which can result in grouping. So on one hand, you could have proximity to be a reason. When there are objects or artifacts in the image which are simply close to each other and these groups lie in different parts of the image, that could result in one kind of a grouping. Or it could just be the similarity of the objects themselves. Some objects are hollow circles, some objects are filled circles, and just because these objects are different, they get grouped differently when we perceive this image. Other factors could be parallelism. If there are groups of lines that have similar properties in terms of parallelism, we end up grouping them. Or another option could also be just symmetry. Just seeing artifacts in a symmetric sense makes us group them in one particular manner. Further, you could also have similarity of a different kind. You could have a common fate in terms of these arrows telling you where these dots are going. So in the second example here, all these dots are more or less lying in a straight line, but the arrows let us group them differently. So in a sense of where they're going to go along the direction of the arrows gives the human visual system a cue to how they should be grouped. Or it could be purely because of a common region that was already marked as a circle. It could be due to continuity of artifacts. It could be due to closure of artifacts. As you can see, there are many factors that result in human perception viewing things as groups. And Gestalt theory is fairly descriptive. It lays down various different rules and principles that could lead to grouping when humans perceive images. However, these rules by themselves are not clearly defined enough to become algorithms. So you really cannot take the rule directly and implement a pseudocode for that rule that could help you find, say, groups in an image. So for the rest of this lecture, we're going to talk about that task called image segmentation, where we try to group similar pixels into different groups. You could call this akin to clustering, where you group different pixels into their own clusters. So a significant part of this lecture is taken from David Forsyth's book and Selinsky's books, and we will share these references at the end. One of the oldest methods for image segmentation is known as watershed segmentation. This was developed way back in 1979. And image segmentation, remember, is the task of grouping pixels in an image, right? So that's the task that we are looking for. The watershed segmentation method segments an image into what are known as catchment basins or regions. It goes along with the name, that's why it's called watershed segmentation. That will become clearer in the next slide. So you can view any grayscale image as a 3D topological surface. So for example, if you have this grayscale image, very similar to how we viewed an image as a function way back in one of the earlier lectures. So you can view an image as a 3D topological surface where the whiteness peaks at these beveled locations, and the whiteness subsides in other locations, and the dark areas are where you have black pixels in the original image. What watershed segmentation tries to do is to segment regions, segment the image into regions with a conceptual idea of rainwater flowing into the same lake. So you're going to create a methodology where you're going to assume that you're going to flood water into your image, and wherever you have catchment basins in the image, imagine this 3D topographic representation of the original image. Wherever you have water stagnating, those groups of pixels form segments. Let's see this in a bit more detail. So you identify various local minima in your image. Remember, local minima as simply values where are pixel locations where your image intensity value is low. Remember again that image intensity can lie between 0 and 255 or 0 and 1 if you normalize the values in the image. So you take certain neighborhoods, say whatever 5x5 patch or 7x7 patch, whatever that may be, and using that process you find out local minima that lie across the image, and you flood the landscape from local minima and prevent merging of water from different minima. So which means you would start with a local minima and slowly keep expanding, which is equivalent to flooding here, until you go to a point which is reachable in the same number of pixels from another local minima. So that's where the boundary between these two regions would lie. So this simple process results, there's nothing very fancy about this other than what I just mentioned. So this process results in partitioning the image into catchment basins and the watershed lines. Remember, this method was proposed in the late 70s and it was used for many years to segment images into various parts. It was generally applied on image gradients rather than the image itself. Just to give you a visual example, so the original image is this one. We ideally want to group the pixels. So you first take a gradient image. Now you know how to take a gradient image. You run an edge filter on the original image. So now the watersheds of your gradient image are given in your bottom left image, and you finally refine and get your segmentation output and put it back on the original image in the last image. A simple method, but works rather effectively. However, it does have some limitations. If there is a lot of noise and irregularities in the image, for example, let's say you have a heavily textured image, so you can imagine a lot of undulations in the texture of the image, or if there is noise in the image, you're going to end up with something like this, because there are going to be a lot of catchments. So now trying to flood those areas will lead you to many watershed lines which separate many different regions, resulting in what is known as over segmentation. So keeping this in mind, watershed segmentation is typically used as part of an interactive system where a user points out a few different centers in the image, and then the algorithm floods from those centers alone, not worrying about other centers that could be in the image. So this idea can help overcome the limitation of over segmentation. If you'd like to know more, you can read chapter 5.2.1 in Selesky's book. This is one of the earliest methods. Since then, there have been many methods that people have developed, and one could broadly categorize methods into two kinds: region splitting and region merging. In region splitting methods, as the name suggests, the idea is to start with the image and then keep splitting it into finer and finer regions. We'll see one example of this method a little later in this lecture. The other kind, which is a bit more popular, are what are known as region merging methods, where you start with a pixel as a region and keep merging similar pixels and forming regions, and you can keep going forward all the way till the complete image. So here is an example of an image which has been merged into groups of pixels. Groups of pixels are also sometimes called superpixels. And this is sometimes generally used as a pre-processing step for higher level segmentation algorithms. One of the popular methods to do image segmentation was graph-based segmentation, which was proposed in the early 2000s by Felsen, Schwab and Hutton-Locher. They proposed a graph-based segmentation algorithm which used dissimilarities between regions to find out which regions to merge in a given iteration. So if you considered an image as a graph G with vertices V and edges E, so you have a set of vertices and a set of edges, and the pixels form your vertices initially, and edges are defined between adjacent pixels. So we define a pixel to pixel dissimilarity metric. For example, this could be based on the intensity values in these two pixels. You could also define this using more sophisticated mechanisms by probably taking a neighborhood and taking oriented gradients and so on and so forth. But whatever be that measure, you have a pixel to pixel dissimilarity metric, which is defined as W of E, which is the weight of that edge joining those two pixels on which we are defining the dissimilarity, where edges E is given by V1, V2, where V1 and V2 are 2 pixels. For example, this dissimilarity metric could be the intensity differences between the n8 neighbors of both these pixels. When we say n8 neighbors, you take a 3x3 neighborhood, and excluding this central pixel, you will have 8 different neighbors. We are calling that as n8 neighbors. So you take 2 different pixels, take their n8 neighbors and find their intensity differences. That could be one way of computing W of E. Once W of E is defined, the method defines a quantity called internal difference for every region C. Initially, remember, the region C would just be a pixel, but in future iterations, a region could be a collection of pixels. The internal difference is defined as the largest edge weight in the region's minimum spanning tree, which means if you have a bunch of different pixels, you find the minimal spanning tree of the bunch of pixels that you have. Now you take the largest edge weight in the minimum spanning tree. We're going to define that as internal difference. To some extent, that's going to be the largest edge weight in that region. It's just a simplified way of saying that. That's one quantity we're going to define. Another quantity we're going to define is called minimum internal difference. Minimum internal difference is given by, if you had two regions C1 and C2, the minimum internal difference between these two regions is given by minimum of the internal difference of C1 plus tau of C1, where tau of C1 is some manually chosen penalty. So I'll explain that in a moment. And then the second quantity is the internal difference of C2 and tau of C2. So tau of C1 and tau of C2 could just be, say, the number of pixels that you have in the region, maybe normalized based on that, or so on and so forth. So you have a quantity and you take the minimum of both these quantities. So you have region 1 for whom you define its internal difference plus some penalty, region C2 whose internal difference and its corresponding penalty, and you take the minimum of these two. Once you have this, for any two adjacent regions, which have at least one edge connecting any of their vertices, we define a quantity called diff of C1, C2, which is given by the minimum weight edge connecting these two regions. So for example, you consider all edges V1, V2 such that V1 comes from region C1 and V2 comes from region C2. So all edges between those two regions, and you take the minimum weight of the edges that connect these two regions. With these quantities defined, the method defines a predicate D for any two regions C1 and C2 as if diff of C1 and C2 is greater than the minimum internal difference between C1 and C2, then you say it is true, otherwise you say it is false. This illustration should help you understand this a bit better. Remember, diff is the minimum edge weight between two regions, whereas minimum internal difference is a minimum internal difference within each of these, between C1 and C2, whichever is the minimum. So if the difference between the two regions is greater than the minimum internal difference, you do not want to do anything. If it's the other way, regions would be merged. Which means if this predicate turns out to be false, you know that diff is equal or lesser than minimum internal difference, which means C2 is as close to C1 as the farthest separated pixels in C1. So you may as well merge C1 and C2. That's the main idea with this particular method. So to summarize, this algorithm merges any two regions whose difference is smaller than the minimum internal difference of these two regions. Here is an example of how this works using the N8 pixel neighborhood. So you can see that the results are fairly good. The different players get separated reasonably well. Parts of the body get separated reasonably well. If you are more interested, please look at chapter 5.2.4 in Selesky's book. The next method we are going to look at is another popular method called probabilistic aggregation, which was proposed by Alpert et al. In 2007. This method is again a region merging algorithm, and it is a probabilistic approach, as the name suggests, and it uses two different cues: intensity values for the gray level values, as well as some texture content of the specific regions in the image. So initially, the method considers each pixel as a region, and then you assign a merging likelihood Pij. So for every two pixels I and j, there's a likelihood Pij which says how likely are these two pixels to merge. And how do you assign that Pij? Based on their intensity and texture similarities. We are not going to go into each of those details. I will point you to the reference. If you're interested in knowing how exactly it's implemented, you can look at the paper for those details. But it's broadly based on intensity. You know how to compute intensity. By now you know how to compute texture. We talked about it the last time. So the Pij is based on intensity and texture similarities between the two pixels. Now, given a graph in a particular iteration, let's say it's at the s-1th iteration, the graph is given by a set of vertices vs-1 and es-1. So the graph at the next iteration gs, where you hope to merge a few regions, is obtained by you consider a subset of seed node C from vs-1, and you merge nodes or regions if they are strongly coupled to regions in C. So what you would do here is you would consider those pixels. So which means you would say that if you took a subset of nodes in vs-1, whichever other nodes, right, we would ideally consider other nodes which are in vs-1 minus C. So those would be the other pixels in vs-1. You consider those pixels, and for whichever pixels you have summation of Pij j belonging to C divided by summation j belonging to vs-1 minus C Pij. When this ratio is greater than a threshold, you know that there are certain pixels that are quite likely to merge as the pixels in the region C itself. So if this ratio is greater than a threshold, which the paper recommends to set to 0.2, then you merge those regions. And once you merge those regions, you propagate those assignments to the finer level children, which would be the property of any region merging algorithm, and you do this coarsening process recursively. Here is an example of how probabilistic aggregation works in practice. So this is an image taken from Selesky's book. So you can see here that image A is the original gray level pixel grid. So it's a 5 by 5 image. So you can see the interpixel couplings in B image. So a thick edge means a stronger coupling, a thin edge means a weaker coupling. So you can see that the pixels that are white are strongly coupled to each other because of the intensity similarity. Then in image C, you perform one level of coarsening where you combine edges that are close to other edges, that you take one particular pixel when you start, which would be C, then you take all the other Vs minus 1 minus C, of all the other pixels in Vs minus 1 minus C, and then you would try to find out which of them has a higher probability of merging based on intensity similarity and texture similarity again. And then you keep repeating this process. You can see that after 2 levels of coarsening, you get a fairly good estimate of different regions in the image. Moving on to another popular method known as mean shift segmentation. This method is a different approach and it uses a mode finding technique based on non-parametric density estimation. So non-parametric density estimation is a standard procedure that people in machine learning use to estimate the density of any given set of observations. So the feature vectors of each pixel in the image are assumed to be some samples from some unknown probability distribution, and we are going to estimate the probability density function of the image and find its modes. Okay. Remember, in some sense, the modes would be like what we had for the watershed segmentation, although in that case we did a minima. Now we're going to talk about a maximum. And then the image is finally segmented. Once you identify the modes in the image is segmented pixel wise by considering every set of pixels which climb to the same mode as a consistent segment. We'll describe this over the next few slides. So let's consider an example image, as you can see here. So it's a fairly real world image. On the right, you see the representation of the image. So we talked about color spaces in week 1. So one of the color spaces that is popularly discussed is known as the L star, U star, V star, or the LUV color space. So this is simply, for simplicity, a plot of only the L star, U star features of this image, just for simplicity of plotting. So in this feature space, we ideally want to find out what are the modes of the overall distribution of the intensities in the L star, U star space. So how do you find the modes of such a distribution? If you recall your studies in machine learning, you would recall that one of the popular approaches to estimate the probability density function or modes would be through kernel density estimation. So we're going to use the same method here to be able to estimate what is the PDF and what are the modes of the distribution of intensities in a particular space. While we have taken example as the LUV space, you could do such a mode finding in any other space for that matter too. Just for simplicity, we're going to consider a one-dimensional example. So remember once again that this is a one-dimensional signal which can be extrapolated to image as a 2D signal. So the way we would estimate this function is we would convolve the data. Let's assume that you have observations given by these impulses here. So you can see those vertical lines. Those are your observations that are given. So you would estimate your density function f, which is what we want to estimate, by convolving your data, your observations, with some kernel of width h. Let's assume that you have a kernel k, so you could do it as a falling off function where h is the width and you have x minus xi to be your function, your quadratic function that you're falling off over. So convolving your observations with this kernel will give you an estimate of what is your original f function that your observations were coming from. What do we do with this? So to find the modes, mean shift segmentation uses a gradient ascent method with multiple restarts. Why ascent? Because we want to find the maximum of or the modes of that probability distribution. So we start with some guess y naught for a local maximum, which could just be any point. Remember, we are going to perform gradient ascent, which is an iterative procedure. So you start with some point, and at every iteration, you add some constant times the gradient to the previous estimate, and you update your estimate again and again and again. So you have a guess y naught, which could be any random point xi. So we calculate the density or the gradient of the density estimate f of x. We just talked about how f of x is computed using that kernel. How do you choose that kernel? We'll talk about it in a moment. So you have the gradient of the density estimate f of x at y naught, and we take an ascent step in that direction. So the gradient is going to be given by something like this: summation xi minus x g of this quantity, where g is nothing but k prime, or the derivative of the kernel k, which is written on the simple derivative. So the gradient of the density function can actually be written slightly differently. You can write the gradient again. Let's see the previous slide. So this was the gradient that we just had, xi minus x into g of x minus xi norm square by h square, where g is k prime minus k prime, or the gradient of kernel. So we're going to show that this can actually be written slightly differently, where the gradient can be written as summation g, capital G of x minus xi, where capital G of x minus xi is simply the same small g that we saw on the previous slide, into mx, where mx is like a weighted contribution of the x values that you're considering in this particular computation. So xi into g of x minus xi divided by sum of all g of x minus xi's. Why is this a correct way of writing from the previous slide? I'm going to leave it to you for homework. It's not too difficult to find this out. Try to work it out stepwise and you'll actually get the answer. So this vector m of x, which corresponds to the gradient, is also known as the mean shift. It's the difference between x, sorry if you I didn't point you to this minus x here, but it's the mean shift is the difference between x and the gradient weighted mean of the neighbors around x. X is where you place the filter, and x minus xi's are the values in the range of that filter, and you do convolution. Very similar to how we saw convolution earlier. In this case, we are only talking about 1D convolution for simplicity. So the vector m of x is the mean shift, the difference between x and the gradient weighted mean of the neighbors around x. And once you get your mean shift, which is also your gradient in this particular case, subject to a scalar multiple, then your next iteration in your gradient descent, your gradient ascent, you're going to say yk plus 1 is equal to yk plus m of yk, which can also be written this way. Remember, you'll just have yk and x would get cancelled because that's where you're placing yk at this point in time, and you'll be left only with m of yk as the quantity, which will become yk plus 1. And you keep doing this process iteratively, and you would finally reach the mode of the distribution, and then you would find out all the neighboring points which by climbing would lead to this mode will form one segment, Other points which by climbing would reach to other modes would go to those segments. Clearly, this method relies on selecting a suitable kernel width in addition to the kernel itself. We use a quadratic kernel here. What width you choose is also important and will impact the final result, and that is chosen empirically. In the above description, the approach seemed to be color based. We took it in the LUV space. You can also consider other kinds of feature spaces to find the modes in. More interested? Please look at chapter 5.3.2 in Selesky's book. One more method, which is not a region merging method, but a region splitting method, is normalized cuts for segmentation. Once again, a very popular method, was used for many years. Once again, a graph-based method, but a different approach. In this case, a graph representing pixels in an image is successively split into parts. It's not about merging this time, it's about splitting. How do you split it? You mark edge weights between pixels based on their similarity. So if two pixels are very similar, maybe they have similar intensities, you give them a high edge weight. And if two pixels are further apart in their similarity, you give them low weight. So here is an example of such a graph that's constructed. So the goal of this would be to find the min cut. We're not going to work out the entire math here. If you're interested, you can look at the references and learn more about it. But you try to find the min cut, which is going to give you two different regions as shown here. And those edges, when you remove, you get the corresponding two segments, which is your original objective. The min cut is defined as sum of all weights being cut. So you consider two sets A and B, two sets of vertices, and for all I belonging to A and J belonging to B, you add up those edge weights. Wherever you get for whichever choice of A and B, you get a minimum cut value. That is the cut that you're going to choose to divide the graph into two segments. So clearly, as you can observe here, this method only divides two segments at a time. So if you want more segments, you will have to do this more and more times, or probably use other heuristics if you wanted to combine them later into fewer segments. But one of the problems with using the min cut is that it can also result in trivial solutions. Why so? Can you think about it? Why does this min cut problem result in trivial solutions? The answer is very simple. When A consists of, say, only one pixel and B consists of, say, another region of pixels, this summation may be restricted to a smaller set and hence may have a smaller value when you sum all of them up, which means min cut could favor regions where there's only one pixel on one side, which may simply be an outlier and may not really form a good segmentation for the image. How do you overcome this problem? This problem is overcome by a method called normalized cut, which improves the min cut problem. And the normalized cut is defined by cut of AB by association of AB plus cut of AB by association of BB. We'll see in a moment what they are. Association is defined again as sum of all the weights in A and B, where association of AB is given by association of AA plus association of AB. It's the sum of all of the weights. And now what you've done by doing this association of AB and association of BB is to ensure that the denominator contains the number of pixels. So in each of these regions. So if there was only one pixel in one region, Remember that one of these quantities will become very high as against another region which had many more pixels where the denominator will pull down the value. This ensures that you don't get trivial solutions such as what you saw in MinCut, but you get more useful solutions in practice. So the normalized cut happens to be an NP-complete problem, but there are approximate solutions to solve this. It's slightly more involved, but you can look at the paper called Normalized Cut and Image Segmentations if you're interested in how the method is actually implemented. That this is the overall formulation. Here is an example of how normalized cuts works. So this is the input image, and you can see the various different regions that get segmented using normalized cuts in over the iterations of the method. There have been many other methods for image segmentation too, such as simply using k-means clustering. There have also been methods based on Markov random fields and conditional random fields, and many more. If you want to have a detailed understanding, please read chapter 5 of Selinsky's book. There are more references at the end of this lecture too. But the question that we're going to ask now is, do we really need all of these segmentation methods? So I think the entire course is based on deep learning for computer vision. Aren't there deep learning methods that can segment images today? Do you really need all of this? It is a valid question. For many tasks today, you do not need these methods. The purpose of covering these topics is to give you a context of computer vision in the pre-deep learning era, but some of these methods have also been used in the deep learning era. For those of you who are a little bit more aware about these areas, the earlier methods of deep learning that were used for detection of objects, which means given an image, you try to find an object and draw the bounding box as to where in the image that object lies. That is the task of detection, and there could be multiple instances of objects or multiple objects in an image. For the initial methods of deep learning for object detection, it was these kinds of segmentation methods were actually used to generate what were known as region proposals where the objects could lie. As I said, one of the first RCNN, which is a region CNN work that was used for object detection, used a min-cut segmentation method known as CPMC, constrained parametric min-cuts, to generate region proposals for foreground segments. We will talk about this in detail when we come to that section of this course. But that's the reason why image segmentation is useful for you to know at this time. Segmentation can also go beyond images into videos. If you go into videos, the principles for the methods are very similar, although there's a third dimension that comes into the picture. But the kind of tasks that one wants to solve in videos is, say, short boundary detection, which is an important problem in video segmentation, where you have to divide an entire video into shorts. Remember that if there's a very long video and you want to understand the video, let's say you have a movie and you want to be able to understand the movie by automatically parsing the video in the movie, you first have to divide the entire movie into shorts and then try to analyze each shot for understanding the scene, understanding the characters, so on and so forth. So that's an important task in video segmentation. Another important task with videos is what is known as motion segmentation, where you may want to isolate the motion in the video of an object. So you could be wanting to isolate a person running. For example, there's a football game and you want to track a person moving with the ball from one end of the field to the other end of the field, or you may want to track a car, so on and so forth. So for further information on this, please look at chapters 15 and 17 of the David Fawcett book in the references for this course. That concludes this lecture, which gives you an overview of how image segmentation methods were used in the pre-deep learning era. Some of them, as I said, were used actually even with deep learning methods, although not as much at this time. But for more readings, please do read these references given here. And recall, we left one derivation as homework for you. Go back and see how to derive the final expression for the gradient of the kernel density function used in the mean shift method. There are some references.